Hello everyone, welcome back to my channel. So in today's video, we're going to continue on the topic of heat exchanger network design using Aspen Energy Analyzer. If you still remember, in my previous video, I decided to divide this topic into three-part videos. The first part of the videos is we just simply use the software to create a hot and cold composite curve. And then in the second part of the videos, which we will do today, we're going to create our own heat exchanger network design using Aspen Energy Analyzer. And of course, in the final part or on the third part of the video, we're going to let Aspen Energy Analyzer to using whatever algorithm that they have to propose their own design for us to evaluate whether it's suitable or not for our case. So yeah, let's begin. All right, I'm going to use the same design problem that I used in my earlier videos, but for the sake of refreshing your memories, basically in this design problem, we have 4 streams that need to be heated up or cooled down, and we need to design our own heat exchanger network. Of course, a few important thing to look for here is what is our delta T minimum. We're going to use delta T minimum of 10 degrees Celsius. Our cold utility is basically a cooling water. We're going to use a default condition provided by the software. And of course, we will use our hot utility. We're going to use a high pressure steam as our hot utility using the same default condition as well. As I said earlier, we have 4 streams, 2 hot stream and then 2 cold stream. The first stream need to be cooled down from 170 to 60 degrees Celsius, and then the heat load is 330 kilowatt. The second stream here need to be cooled down from 150 degrees Celsius to 30 degrees Celsius, and then the heating load is 180 degrees Celsius. 180 kilowatts, sorry. The third stream here is a cold stream, need to be heated up from 30 degrees Celsius, 20 degrees Celsius to 135 degrees Celsius. And then the heat load is basically 230 kilowatt. And then lastly, our fourth stream is basically need to be heated up from 80 degrees Celsius to 140 degrees Celsius. And then the heat load is 240 kilowatt. All right, let's check out our next slide. All right, as I said earlier, Aspen Energy Analyzer, we can design our heat exchanger network manually, meaning that we use whatever features that are available to recreate our heat exchanger design to recreate our hand design. For example, as shown in the slide here, in the software. The second features is basically Aspen Energy Analyzer. They have their own, I would say, algorithm. I'm not going to go into detail, but basically this algorithm allows you or allows the software to propose more than 10, 1, 2, 3, even more than 10 actually, design that they think can be proposed to you based on whatever cold and hot stream that are available or that you provide. In this video, we're gonna begin with the first option where we will design our heat exchanger network manually. So what do I mean by this is basically I have my own heat exchanger network design that I prepared manually, and then I'm going to use whatever features that are available in the software to recreate those. Of course, you can just simply do whatever inside the software, but I think for this purpose, it would be a good idea to just simply show you an already completed design that I prepared earlier. Okay, as you can see here, as you can see on the slides, this is the heat exchanger network design that I have prepared earlier based on some references. I'm not going to go into details on how do I get this particular design. Maybe different people will design it slightly differently, but this is my design. I think this is the simplest one. But the idea here is not to show you how to create this, But the idea for today's video is just to show you what are the features that we can use in the software to recreate whatever hand design that I have prepared earlier. But as I said before, I'm gonna create another video where showing you how do I create this heat exchanger network design manually, all right? But to summarize, I have a heater here providing 20 kilowatt of energy. I have a heat exchanger um, number 1, heat exchanger number 2, heat exchanger number 3, heat exchanger number 4, and then 2 cooler with a total heat cooling load of 60 kilowatt. And of course, I have a split here. Basically, I split the stream into 2 parts where the heat load of this particular stream is divided into 2, and then this will be given. This will be, I would say, they will each of this split stream will receive the same amount of heat load from hot stream number 2 as well as hot stream number 1. So as I said, we're going to recreate this in our hand design. And of course, we're going to determine what is the heat exchanger surface area, what is our capital cost, utility cost index, payback period, as well as cost saving. All right, I think I have described all of it. So yeah, let's go to our Aspen Energy Analyzer software. All right, guys, as you can see right now, this is my Aspen Energy Analyzer, I would say, a window. The first thing that I will do is I will just simply go to the managers, go to Heat Integration Manager, and then I'm going to create HI project, Heat Integration Project. So I'm going to click Add. All right, they will create a folder, I would say, having HIP1, Heat Integration Project number 1, and then I will need to, and then they have prepared a scenario 1. So in the scenario 1, I will click, and then as you can see here, I'm going to make it bigger a bit. Under scenario 1, I will need, first I will need to define my stream. I have 4 stream, H1 from 170 to 60, and then the enthalpy is 330 kilowatt. As I told you earlier, this part of this step has already been described in my earlier videos. So to those who want more details, please check out my earlier videos. But I'm going to do this fairly quickly because I have described them in my earlier videos. So H2 need to be cooled down from 150 to 30. And then the enthalpy is 180 kilowatt. Let me rename this H2. All right. And then I have a C1. Need to be heated up from 20 to 135. And then my enthalpy is 230 kilowatt. And then C2, cold stream number 2 need to be heated up from 80 degrees Celsius to 140 degrees Celsius, having enthalpy of 240 kilowatt. All right, now that I have defined my stream, hot stream and cold stream, I need to check my delta T minimum should be 10. Now this is 10, but if you want to set 5, this by all means, just click this guy, click this box, and then just type number 5 and hit enter. The next thing that I need to define is my utility stream. As you can see, without my utility stream, I cannot heat up. I cannot provide the necessary heat and then cooling to complete whatever network design that I desire. I'm going to use a high pressure steam, default condition, no change. But if you want to change, by all means, please do so. I have no issue with that. And then the second cool utility is where's my cooling water? So I have cooling water here, default condition. So if you decide to use other condition, by all means, proceed with whatever condition that you desire. Now, as you can see, once you have specified your hot and cold utility, this becomes sufficient, meaning that utility plus whatever process stream that you have, you'll be able to complete using whatever utility as well as the stream, you'll be able to provide necessary heat or cooling load to complete the requirement. Okay, now that I have prepared all of this, next I will do the design. I'm going to design my heat exchanger network. So I don't want to do anything here, but maybe I should describe what is target. Now, in Aspen Energy Analyzer, you have multiple target, meaning that what are your desired, what is your best design? Now, energy target here basically means what is the best, I would say, energy use, what is the most minimum energy usage? And then you have area target, means that what is the lowest area that you can get from this design, what is the best area that you can possibly achieve, okay, to complete the design, I would say. And then cost index, you can also design your heat exchanger network such that they minimize the capital cost. You can also design your heat exchanger network to provide the lowest number of process unit, which is lowest number of heat exchanger, number of unit, as well as number of passes or number of shell, if you will. But I'm not going to go into details on that. But this is what targets mean. All right, under scenario, we're going to design our own heat exchanger network. So you click scenario 1. As you can see here, you have a plus symbol here. Just click, and then they will expand. You will see a design number 1. Now, if you click design number 1, you will be redirected to this grid diagram. Okay, these are called grid diagram. The dashed line here means that the grid diagram is not yet done, so it's not yet completed. So that's one of the way for you to tell, to know whether this diagram is it already completed or not. Okay, let me make it smaller, this part, so that's easier for us to design. Now, the blue continuous line here is your cooling water. This one is your hot stream number 2, cold stream number 1, cold stream number 2, or the other way around, doesn't matter. And then you also has a high pressure steam, which is your hot utility. Okay, what do we have here on the heat diagram? On this grid diagram, you have temperature and your utility and a hot and cold stream. Now, these are all the necessary features that would allow you to create your own hand design. Let's check it out. Okay, this one is basically, if you click here, it just simply switch the direction of the stream. Doesn't do much, but it just simply change the direction. Maybe the first one, it goes from left to right for the hot stream. And if you click here, it goes from, okay, if you click here, it goes from left to right, the hot stream. But if you click, it goes from right to left. It's just changing direction, nothing much. This is what these features do. Let's see. Okay, this option, if you click, they will tell you what is your pinch temperature. Hot pinch as well as cold pinch. Now, as you can see here, what is my hot pinch? My hot pinch is 90 degrees Celsius. My cold pinch is 80 degrees Celsius. That's it. Okay. I'm going to turn it off. And then this one is where you're going to add heat exchanger. All right. Okay. I'm going to do one right now. Okay. First, if you need to refer the, what is it called? You need to refer the diagram that I show on the side for you to understand what unit did I add. So I'm going to add heat exchanger number 1 first. So heat exchanger number 1, you need to click here. Okay. Now, Aspen Energy Analyzer, they somehow they do it weirdly. What I'm trying to say is the way you need to add heat exchanger network in Energy Analyzer is a bit weird. So what do I mean by that? I'm going to show you. All right. To create to add a heat exchanger network, or to add heat exchanger, what you need to do is go to here. All right. Add heat exchanger. Now you left click. No, sorry, you right click your mouse. Continue holding left click, and as you can see, my cursor become this this symbol, and then I'm gonna add them to my first stream, which is stream number 1. And then, so once you move it to whatever stream, you release your left click. Now you will have this circle. Now this circle, you need to connect to the fourth stream. You need to connect to here, okay? So you just use your right click and then hold the right click until you touches this stream. Now they become like this. Okay, what does it mean here? This stream has already been paired. You already pair this stream, hot stream number 1 to cold stream number 2. Okay, actually hot stream number 1 is basically stream 1 in the slide. Cold stream number 2 is my fourth stream in my slide. I'm going to change the direction. I don't really like it. I like it this way. All right, next, what I need to do is I'm just going to double click this. Now, once you double click this, you will be redirected to this. Okay, if you see your slides, from stream number 1, it goes to heat exchanger number 1, and then it will go out with a temperature of 90 degrees Celsius. So in here, I will write down 90 degrees Celsius, hit enter. And then here, you can just simply write down 170, or you can just simply click tie. Doesn't really matter. Tie here basically means, okay, whatever temperature on the end, okay, before it goes to the heat exchanger, that's the same temperature. So that's what it means. Now, if you refer to the slides, going to heat exchanger number 1, the stream has temperature of 170. Leaving heat exchanger number 1, it has temperature of 90. So this is checks. This checks. Now what I need to do is complete the cold stream. Okay, the cold stream number 4 need initially temperature of 80 degrees Celsius. As I said, you can just simply type 80 here, or you can simply click tie. And then leaving will be 140. Now it's only 140. So as you can see, calculation okay means that it's already do the calculation, no error whatsoever. And as you can see, the DT minimum at the cold end is 10 degrees Celsius. According to our DT minimum, the hot end is higher. So obviously it's going to be higher. All right, close. Now, as you can see, whatever dashed line that you see earlier already changed with the continuous line, meaning that this particular stream is already complete, no issue whatsoever. All right, next I'm gonna add. I think I'm gonna show you my what is called my pinch line. Okay, pinch temperature. All right, the next stream that I will do is I'm gonna add my second heat exchanger. All right, my second heat exchanger is from this particular stream, goes to this particular stream. Again, how to do that? Go to move your cursor here, add heat exchanger, right click, continue right click, move your cursor all the way to this particular stream, and then you release click. Okay, now you will have a second red circle. Now, how can you pair this particular red line with the other blue line? Just move your cursor here, left click, continue left click, and then drag down. You will see a line here, go all the way to the blue line, and then you release left click. Okay, now you have added the second heat exchanger. Do the same, double click. Now you need to solve, you need to add the temperature or heat load, if you know, in order to solve this heat exchanger. As you can see, currently it is underspecified, meaning that you need to provide a sub-specification. Now, if you see your slide, stream number 2, okay, initially at 150, go into the heat exchanger, still 150, you can write down 150 here, or you can simply click tie. Leaving heat exchanger, it is at 90 degrees Celsius, not 30. So you need to type 90 degrees Celsius. Now these are done, but still partially calculated. It need to be solved. So you need to provide information on the cold stream. Now cold stream, initially it is begin at 80 degrees Celsius. It goes into the heat exchanger. and then it leaves heat exchanger 125. It is auto-calculate. Once you specify enough, the rest will be auto-calculated. Again, DT cold end is still 10 degrees Celsius. On the hot end is higher because the pinch, the minimum temperature difference is 10, no changes whatsoever. Now this become calculation okay, so you can close and proceed with the next one. All right, the next one, what I will do is I will complete the one on the left side, on the hot side. On my hot side, I just simply add a heater. So again, the same thing, add heat exchanger, right click, continue right click, move your cursor to the blue line, release left click, and then you add, and then you provide hot utility to complete the desired heating. And then you right click, continue right click until you reach to the red line, release right click. Now as you can see, they have different symbol, means that this symbol is a heater. I mean, it's being provided by the heat load is being provided by your hot utility. Now again, you need to provide the same information. In this case, I'm gonna tie this one because before it enters, after leaving this heat exchanger, it is at 125. So going into here, it should be 125. Also, I can click tie, and then leaving the heat exchangers, it goes to 135. So I click tie also. Now calculation are all okay. Just simply close. Now as you can see, this portion become blue, continuous line, solve, 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 solve. Now what I need to do is complete the rest on the cold end. Now at the cold end, I need to add my third heat exchanger, where this particular heat exchanger will be paired from this stream to this stream. But if you remember, this stream has a split stream. If you know what I mean. Please refer the slide. You will see there's a split stream. How can I add split stream in this case? So it's quite simple. Move your cursor here. Move your cursor here. You have add split, right? Again, the same thing. Right click, continue right click. As you can see, your cursor changes its shapes from arrow to this circle symbol. Move your cursor until you touches the blue line. Release the right click. Release right click. Now you have this particular dot, right? So just double click this dot, then it will be split. Right? Just double click the dot, it will be split. All right, next, what I will do is I will add heat exchanger for exchanging heat from this stream to one of these split. So move your cursor here, add heat exchanger, right click, continue right click, move your cursor here anywhere, or if you here also can, doesn't really matter. Release right click, and then move and then left click, continue left click until it touches this blue split line. Release left click. Now solve this particular heat exchanger design. Double click. Now for this particular stream, it goes at 90 degrees Celsius. So click tie, and then it leaves not at 60, at 70 degrees Celsius. Now it's partially calculated, so meaning that you have to solve the blue curve. So in this case, it goes to 20 degrees Celsius right away, all the way to 20 degrees Celsius. Click tie, and then it's done. Repeat the same thing for the next stream. Right click, right click, continue right click, move your cursor here, release right click, you have the red circle. Okay, move your cursor to the red circle, left click, continue left click until it touches the second split, release left click, and then of course you need to solve this stream as well. So double click, For this particular stream, it is the hot stream enters at 90 degrees Celsius, so click tie, and it leaves not 30, it leaves at 50 degrees Celsius, enter. Now it is partially calculated, so you need to provide information on the second stream. And then it need to be heated up from all the way from 20 degrees Celsius. So click tie, and it's done. Now you have done this. As you can see, almost all of it are becoming becoming continuous line from a dash line. This dash line need to be solved. So how can I do that? I just need to add heat exchanger. Right click, move your cursor here at my heat exchanger, and I move it to coal utility. Okay. Now, if it goes to the coal utility, this particular I would say symbol become blue, right? Meaning that it exchange heat. No, the hot the heat remove is done by coal utility. So you double click. In this case, just simply click tie here, click tie here. It's done. And then solve the last one. At heat exchanger, right click, continue right click, move your cursor here. Left click, continue left click, move your cursor to the coal utility. Solve it. Again, the same thing, click, tie, and then done. Now, as you can see, everything complete already, where all of the stream are accounted for. All of the stream has been has turned from dash line to a continuous line. And then, as you can see, it become green. Infeasible heat exchanger network is 0, means that there are no infeasible network. Number of heat exchanger not calculated is 0, means that all of the pair here has already been calculated. And then unsatisfied stream is basically stream that are not done or partially specified. 0 means that we have no error whatsoever. Okay, now that we have done this, where can I get all of the information related to my design, right? So if you go here, let me bring it up. Now this is my heating cost, cooling cost, operating cost, capital cost, total cost. This is your design. Heating duty, cooling duty, number of unit is basically number of heat exchanger. 1, 2, 3, 4, 5, 6, 7. So 7. Number of shell is 16. Basically, how many passes? I think, if I'm not mistaken, I'll check it out. Total area is 370. Now, percent target, what does it mean here? Percent target here means our design, how can I explain this? Okay, percent target here means what are the okay, 100% means you are approaching to the best design. Okay, best heating the best, the most ideal heating requirement. In this case, right, my heating requirement is 7.2 to the power of 8 kilojoule per hour. Percent target is 100%, means that it's close to is basically closest to the ideal case. That's the best explanation that I can provide. Same goes with the cooling. Now, number of unit is 7, but percent target is 87.5, means that if you want to get 100%, actually there are a better design that can give you the least number of unit. I will explain why. I will explain later, I guess. But in this case, I have 7 unit, but the best design is probably a 6 unit. Number of shell are the same thing. I have more shell, more unit than the best case. And the total area is 370, 103.5%. Basically, it is higher than it's basically 3.5% higher than the ideal case, if you know what I mean. All right, how can I get all of the best case, right? So as you can see here, these are 7, these are 16. So how can I know what's the best case for area? So you go to scenario 1, you go to the target, right? So as you can see here, target, if the best target, the best area target that you can achieve is 306 meter square for shell and tube heat exchanger, or 253 if you're dealing with a counter current heat exchanger. Now mine is 317 if I'm not mistaken. Now it's much higher than the best case, but it's at least close, really close. So it's good. I think it's good enough. Now my heating here is the same with mine. So since it is the same value, so it's 100%. I mean that is exactly following the best design. Now, what is the number of unit target? The best one is 5. Now, but mine is 7, right? So if your target is you want to have the least number of unit, you need to have 5 units. So how can you design to have 5 units? It's completely up to you. I don't know, but that's how it is. Now, the capital cost index, this is the best index that you can achieve. But in my case, it's slightly different, it's slightly higher because it's my design. Okay. My design is like I decide how I exchange it. So it's up to me. But ideally, it should be closer to the most ideal case. All right. Now, this is my design. I think I have covered all of it. Oh, yeah. If you want to see your heat exchanger area, so click here. Now, this is your heat exchanger area, individual heat exchanger area, and then number of shell. Number of shell here, if I'm not mistaken, I will check again. Number of shell here means number of passes. Again, I will check one more. I will check whether my interpretation is correct or not. But I think it is the number of passes. Now, area E100 is basically, I think this one. No, sorry, E100 is this one. So you need to check what is the assigned name for this heat exchanger. This is number 1. This is 101. So 101 here. Basically, it follows the basically E100 is the first heat exchanger that I pair, which is this that I add. This is the second one, the third one, the third one is this one, I think. Yeah, E102, because I add this one I add this one first, I add this one second, I add this one third, I add this one fourth, I add this one fifth. So 0, 1, 2, 3, 4, 5, 6, something like that. But as you can see, these are the capital cost index, capital cost, area index, and share. Again, how the cost is assigned is basic, and how the capital cost is calculated. You need to provide the actual parameter value. You cannot just simply willy-nilly use this number unless it is the correct parameter. If it's not the correct parameter, maybe you are using Malaysian ringgit or US dollars, or maybe heat exchanger using stainless steel heat exchanger, probably will have a different value. So again, I don't really want to go into details on how you want to design heat exchanger, how it affects the costs and stuff like that, because this is not really the main point of this video. But what I'm trying to say here is, if you refer to the summary, right? If you go to cooling cost per second, there it doesn't really mention whether is it a euro, whether is it a pound sterling, whether is it a Malaysian ringgit or whatsoever, right? That's why, because they don't really give I would say the actual price or the actual cost index in terms of, like, say for example, whatever currency that you use. So it is completely your responsibility to make sure that the cost index is correct. So how do you want to do that? Just go to the scenario 1. No, actually, yeah, go to scenario 1. Under utility, you need to provide your own cost index. Right now, if it's in Malaysian dollars, Malaysian ringgit, so you have to change this to Malaysian ringgit and stuff like that. Same goes with the capital cost. So if capital cost, let's see, these are total cost index, options, let's see. Again, I don't really remember. Sorry, under economics, I think. Now, these are the heat exchanger area. These are all of the capital costs. Capital costs for fired heater, heat exchanger, they have this correlation. This particular correlation may not be applied for your case. So you need to change it. So it's completely up to you. How do you want to design this? These are all of the default values for ROI. Plan years, 5 years. You probably need to change to 20 years, whatever. ROI, hours of operation, stuff like that. It's completely up to you. It's your responsibility to make sure these are all correct and this apply to your case. But anyway, I think that's pretty much it. All right, one last word from me before we go to the slide to conclude whatever things that we have learned. On my third videos, I'm going to show you how we can let Aspen Energy Analyzer recommend a design and then see whether their recommended design is good or not for our case. All right, I think that's it. So let's go back to our Aspen Energy Analyzer slide for conclusion. Alright guys, as you can see right now, this is our final version of final design of our heat exchanger network. Again, this is my design. Maybe people might design having a different constraint. Maybe they prefer to have the lowest number of area, or maybe they prefer the lowest number of unit rather than having the least amount of utility usage or cost, stuff like that. Again, this is my design. What I'm going to show today, what I'm showing you today is just simply it's just showing you what are the features available in Aspen Energy Analyzer to allow you to design your own heat exchanger network. Right? Okay, these are our results. So these are performance of my own heat exchanger network design. Heating cost is basically 0.18 maybe US dollar per hour. Again, depend on whatever currency they use. So you have to make sure that you are using the correct currency, using the correct price index. Heating load is 20 kilowatt, same as if you refer to our earlier videos, it is exactly 20. Capital cost index, cooling cost index is basically 0.045 dollars per hours. Again, ringgit per hours, whatever. Cooling load is 60. Area target. Okay, this is what I meant. The best for this particular scenario, the best area, the smallest area that you can achieve if you are using a shell and tube heat exchanger is 306. But in my case, my design uses a slightly higher area, but the advantage of mine is I recover almost all of the my energy recovery is basically maximum energy recovery. And then for my case, my number of unit is 7. My number of shell, okay, again, shell here does not mean that the shell side of your heat exchanger is basically the number of passes. Again, I will double check whether the shell defined as Aspen Energy Analyzer, does it define as the number of passes or really it's number of shell? But I think it's number of passes, because number of unit here is number of heat exchanger. And of course, you have your own area for each of the heat exchanger design. And the total of this is around 317. Okay, these are individual area of your heat exchanger. Alright, I think that would be all from me. If you like the videos, give it a thumbs up. Consider subscribing to my channel. If I say anything wrong when explaining this video, please let me know. Again, I will check whether the shell, the term shell defined Aspen Energy Analyzer means shell, or is it number of parcels? I will check it out. I will check it. For my next video, for my third part, I think I will upload 2 weeks from now. Next week, I'm gonna show a video on how to do a problem table method, I guess, manually, and then I'm gonna upload my final part of my Aspen Energy Analyzer. All right. Thank you all for listening, and yeah, again, hit subscribe, hit likes, and I will see you guys again in the next video. All right. Bye bye, and have a nice day.